Hi. Last lecture we have discussed logic gates. In that basic logic gates we have discussed. In this lecture we will be discussing the universal gates, special function gates, and we will see some implementation of some logic functions also using the gates. Let us start with the universal gates. Keep the heading universal gates. Universal gates. Right. First, let us write the fundamental definition of the universal gate. What is the fundamental definition of the universal gate? Write down. In a universal gate, we can make any logic function. Using only one particular type of gate. We can make any logical function. We can make any logic function using only one particular type of gate. Then it is called universal gate. Right. Please understand. Say you want to make any function. You have only one particular X type of gate. You don't have any other type of gates. Only X type of gates. So I want to make any function using only this X type of gates. Say NAND gate is available with me. Using only NAND gates without using any other gates, if I am able to make a function, then it is any function, then it is said to be universal gate. Say NOR gate is there. Using only NOR gate, I don't use any other gate. Using only NOR gates, if I am able to implement any logical function, then it is said to be universal gate. Then how to check whether a gate is universal or not? What are the basic gates we have? AND gate, OR gate, inverter. So any function is combination of AND or inversion only. So if you are able to make AND gate, OR gate, inverter using this particular gate, then it is said to be universal gate. So simply what is that? If you are able to make AND gate, OR gate, inverter, then it is a universal gate. I'll prove that universal gates. Okay, let us start with the NAND gate, which is the first universal gate for us. Okay, NAND gate. What is the NAND gate? You can understand here inversion of AND is called NAND gate. Say for example, you have A, B, and inversion of AB is called AB bar. So 0, 0, 0, 1, 1, 0, 1, 1. So you know AND operation we have already discussed in the previous lectures. What is AND operation? Both are 1, then only 1. Then what is the inversion of this? Right. 0 inversion is 1. Okay, 1 inversion is 0. So this is what we call it as NAND gate. What is NAND gate? Inversion of AND gate. Say, take one AND gate. At the output of the AND gate, take one inverter. Then what we get, it is called NAND gate. Say A, B, AB and AB bar. So A, B, what is the output? AB whole bar. Okay. But please understand one important point. For understanding purpose, we explain NAND is nothing but AND followed by inverter. But in practice, what is NAND means is, suppose you want to make a NAND gate. We never take one AND gate and one inverter and make a NAND gate. NAND gate is directly available. Say you are making a gate with transistors, NAND gate, NOR gate, they are always available. We discussed very clearly in the logic families. So NAND gate, NOR gate, these gates are directly available. We don't make it with AND gate and inverter or OR gate and inverter. Okay, so these are directly available. Understanding purpose, we take like this. Now, as we discussed in the previous lectures also, let us see the concept of enable and disable functions. Say I have an AND gate. If one of the input is 1, okay, so other input is, for example, A, what is the output? 1 into A is A bar. So output is inversion of the other input, or you can say when one of the input to the NAND gate is 1, it will work like a inverter. Let us take this. One of the input is 0. 0 into anything is 0. Whole bar is 1. So you can understand, already we discussed in the AND gate also enable disable concepts. Here the output is depending on other input. Here when one of the input is 1, your output is depending on the other input. When one of the input is 0, output is constant or independent of other input. Other input can be anything, you are getting the same output. Then it is called as disable condition. So now see here. Is it similar to AND gate or not? AND gate also enable input is 1. Output may be different. What is the enable input of AND gate? 1. Disable input is 0. So enable disable inputs are similar to AND gate. So you can say you can understand unused inputs of NAND gate will be treated in the same way as unused inputs of AND gate. Okay, suppose you have a 3 input NAND gate, you used only 2 inputs. What about the other input? Last class we discussed about the AND and OR gate conditions of unused inputs. Same is applicable here also. We can apply the same concept because the enable disable inputs are same in both the cases, right? I'll give you the point. First copy this part. One second. AB bar. Right. Now, please make a note. Write down unused inputs in the NAND gate. Unused inputs in the NAND gate are treated in the same way as unused inputs in the AND gate, okay, unused inputs in the AND gate, since the enable and disable inputs are same. Okay. Now, in the last class, we have discussed first lectures. We have discussed one important point. What is that? NAND and NOR does not follow associative property. Let us see that. Suppose I have NAND gate A, B. What is the output? AB whole bar. Take C. AB whole bar into C whole bar. Right? Now, same I take BC first. Now what is the answer? BC bar A into BC bar whole bar. You can understand both are not same. So here NAND is not associative. Already we have discussed this point when we discussed the basic Boolean laws. It is proved now. AB bar into C whole bar is different. A into BC bar whole bar is different. Here order is having a priority. Okay. Similarly, you see here, suppose earlier we discussed AND gate. What is 3 input AND gate? Can be made with 2 input AND gates. Say A, B, C. What is the output? A, B, C. But here A, B into C. What is the answer? A, B into C. Okay. But same, you cannot apply this logic to NAND gates, because if you take 2 NAND gates, it will not form a ABC whole bar, or it will not form a 3 input NAND gate. Then how to make 3 input NAND gate? See, if you want a 3 input NAND gate, directly it may be available. So you want to make it with 2 input gates. Take one second. Take one AND gate, A, B. Output of this you connect to one NAND gate. Then what is the answer? AB into C whole bar, because it is AB. So this into this whole bar. So this is the way to make a 3 input NAND gate. So 3 input NAND gate can be made with 2 gates, but one should be AND gate, one should be NAND gate. You can make this AND gate also with NAND gate, I will show you, but you cannot make a 3 input gate with 2 input NAND gates. That is the important point. And NAND does not follow associative property. Same logics are applicable for NOR also. I'll explain that NOR next. Okay, copy this first. Right. See, now let us discuss about the next gate in the universal gate. I will prove it as a universal gate. First, let us understand concept of the NAND and NOR gates. Then I will prove they are universal gate. Okay, gates. Okay. Now keep the heading NOR gate. You can understand, similar to NAND. NAND means inversion of AND gate. NOR means inversion of OR gate. So here, you take A and B. What is the output? Inversion of OR operation. AB whole bar. A plus B whole bar. 0, 0, 0, 1, 1, 0, 1, 1. Okay, what is A plus B? 0 plus 0 is 0. Bar is 1. 0 plus 1 is 1. Inversion of OR. Inversion of OR. Inversion of OR operation. So this is output is inverted output of the OR operation. You can say symbol wise it is OR gate followed by inverter. A plus B, it is A plus B whole bar. It is equal to this one. You give AB here, A plus B whole. As I told you for NAND gate, same is applicable here also. What is that? You can understand it, NOR gate, NAND gate, they are directly available. We don't make general practically with the OR gate followed by inverter condition. or AND gate followed by inverter in the previous case. Okay, they are directly available. Now let us see the enable disable inputs. One second. Right. Now, if one of the input is 0, what happens? 1, what happens? Let us see. If one of the input is 0, another input is A plus 0 is A, inversion is A bar. Output is inversion of other input. So, output is depending on other input here. If one of the input is 1, 1 plus anything is 1, inversion is 0. So the disable input here is 1 because the output is independent of other input here. So they are same as or. So you can understand here enable and disable same as OR gate. So unused inputs. Already I have given the same lines when we discussed the NAND gate. So let us write it here directly. So unused inputs, okay, treated similar to OR gate in NOR gate. That's all. So this is the basic concept. So enable and disable inputs are same as OR gate. So unused inputs are treated similar to OR gate in the NOR gate also. Okay. So enable disable inputs are same. You can write this point. First copy this and lastly write this. So that you can also prove like previous case. It is not satisfying associative property and you cannot make a 3 input NOR gate using 2 input NOR gate. Same whatever we discussed for NAND similarly is applicable for your NOR gate also. Okay. Now copy this, then I will prove it the NAND gate and NOR gate as a universal gates. Right. Copy it. Okay. Right. Now let us prove that NAND gate and NOR gate are the universal gate. Now keep the heading NAND and NOR as universal gates. NAND and NOR as universal gates. NAND and NOR as universal gates. Write down the point. Write down. If you are able to make AND gate, OR gate, inverter using only NAND or NOR gates, then we can prove it as a then we can prove it as a universal gate. Then we can prove it as a universal gate. Then we can prove it as a universal gate, right? Now, let me try to implement the basic gates, AND gate, OR gate, inverter, using only NAND gates and using only OR gates and NOR gates. Then let me prove it as a universal gate. Let me show first using only NAND. Right. First, I'll make inverter. Inverter Y is equal to A bar is the required condition. Then how to get it? Say you have a NAND gate. If you give one of the input as A, okay, two ways you can make it. If other input is 1, what is the answer? A into 1, A bar. This is one way, is the best way actually. Another way is like this. Then here also A, here also A. What is the answer? A into A whole bar, A bar. Okay. A into A whole bar is nothing but A bar. This is how to make a inverter using NAND gate. Let us make AND gate. What is Y? A into B. You can obtain AB with the help of, because in NAND means bar should come. So take 2 bars here. Bar will cancel. What is the answer? AB. So here take one NAND gate. A, B. What is the answer? AB bar. Take one more NAND gate. What is the answer? AB bar whole bar, which is AB. You can understand here, this is AB bar. Here, this is nothing but inverter. Inversion of AB bar is AB bar whole bar, which will give you AB, which is nothing but AND gate. Lastly, let me make OR gate. What is OR gate? Y equal to A plus B. But I need a bar in the output representation. So take 2 bars. Then what is A plus B whole bar? A bar into B bar by DEMUX whole bar. So here you can see bar and only dot. Dot means end operation. So I can try to make it with using NAND gate. So here take one A bar is required. So take inverter using NAND gate. Here B bar is required. Take B, make inverter using NAND gate. Now take these two and connect this into this whole bar is required. So take one more NAND gate. Then what is the answer? A bar into B bar whole bar, which is A plus B. Because I told here this proved A bar into B bar whole bar is nothing but A plus B double bar, which is nothing but A plus B. Okay. So this is how to make inverter, AND gate, OR gate using only NAND gate. So I can say I have proved NAND is a universal gate. So I can make AND gate, OR gate, inverter using only NAND gate. What is the meaning? You can make any function using only NAND gates. Let us make it using only NOR gate, inverter. What is my inversion requirement? Y equal to A bar. So take here also OR gate, NOR gate. You take one input as A, one input as 0. A plus 0 is A bar. Another way is take here common. Then A plus A whole bar will be equal to A plus A is how much? A whole bar. That is your inverter. Next, how to make AND gate. What is Y? AB is required. Take 2 bars. Then AB whole bar. Here I should see pluses because it is a NOR operation. So AB whole bar can be done by De Morgan's A bar plus B bar whole bar. Now you can make it. A bar is required. How to make A bar? Just now we have seen. B bar. Now both of them whole bar. A bar plus B bar whole bar, which is nothing but AB. OR gate. What is Y? A plus B. You can make it with A plus B double bar. How to make double bar? Plus is there, double bar. So blindly take one NOR gate. Then A plus B whole bar. Take one more NOR gate and make it a inverter. Then A plus B double bar, which is equal to A plus B. Okay. So now you can say NAND and NOR gates are universal gates. Why they are universal gates? You can understand. You can make AND gate, OR gate and inverter using only NAND or using only NOR. Here better to remember minimum number of gates required. How many gates are required? Minimum 1 gate is required. Here minimum 2 gates are required. Here minimum 3 gates are required. In this case minimum 1. Here minimum 3. Here minimum 2. Okay. Here I used 2 gates. Here I used 3 gates. Here I used only 1 gate. Please copy this. Okay. See here, you know what is the meaning of this double bar? Any A bar, X bar, whole bar is always equal to X. You can always cancel. And similarly, don't say, sir, can I cancel it here? These are individual bars, whole bar. If we have 2 whole bars or 2 individual bars, then we can cancel. Okay? One upon other. Don't say I will cancel these 2 with this. Okay? This is only right way to cancel it. Okay? Right. I told you when we discuss about your Boolean algebra, I have given you few points. What are they? Other than NAND, NOR, AND, or inversion, XOR, whatever may be, we have 2 functions I have defined. What are the 2 functions I have defined is implication and inhibition. At that stage also, I told one important point. I will prove it later. I told what is that implication and inhibition gates are possible. They are called as universal gate. Okay, not only NAND and NOR gates. These are also universal gates. What are they? Implication and inhibition. Now let me prove it that implication and inhibition gates as a universal gates. Right. Write down the question. Prove that implication and inhibition gates are universal gates. Right. Right. Let me try with first implication. From the previous experience, you know how to prove it as a universal. Just make AND gate, OR gate, inverter, it is a universal. Or you make NAND or NOR also using this, it is a universal. Because NAND and NOR are already proved as universal. What is A implies B? We discussed. A bar plus B. That is, this is the gate representation. It is A, it is B. What is this? A bar plus B. Right. Now, let me make a NOT gate using this. It is very easy. I have A bar plus B. NOT the meaning is I want A bar. So, remove B. How to remove B? Make B equal to 0. So, take A here. Other input you make it 0. And what is the answer? A bar. That is how to make inverter using implication gate. Next, let us try to make OR gate. Now, you have A bar plus B, but I want A plus B. So, what we need to do is take here bar, then it will be A plus B. So, already A bar is available. See here how to make it. A, here 0. What is the output? A bar plus 0. Here bubble means inversion. Okay. Now, for this you give it to B. Then what is the answer? A bar whole bar. What is the answer? A plus B. Okay. Here it is A bar. Here it is A plus B, OR gate. Lastly, let us make AND gate also. What is AND gate function? Y must be equal to A into B. Okay. You can also make A into B like this. Take 2 bars. What is the answer? A bar plus B bar whole bar. Okay, let us make it using this because implication is having plus symbol. So, my function should be in the form of plus symbol. So, A you take it and here you take B, but one implication gate and 0. What is the answer here? B bar plus 0, B bar. Now, you connect these two with another implication gate. What is the answer? A bar plus B bar. Okay. Now, you take it to A bar plus B bar by De Morgan's, which is equal to AB whole bar. Now, you connect this to one more implication gate. Then A bar, another bar. What is the answer? AB. Right? So, I am able to make NOT gate, OR gate, AND gate using only implication gates. Then it is said to be universal gate. Similarly, you can try this part as it is the same. I am not repeating. Inhibition. What is inhibition? A inhibition B is equal to A into B bar, or you can say the gate wise A into B whole bar. Okay. Prove as universal gate. How to prove it as a universal gate? Make inverter, make OR gate, make AND gate. You can say it is a universal gate. Yes or no? So you can try this. So now it is proved, not only NAND gate, NOR gate, these two implication and inhibition gates are also universal gates. So generally what we know is only NAND and NOR gate. So these two functions are also can work as a universal gates. Copy it. Okay. Now it is proved that implication and inhibition gates are universal gate. Okay. Now the last two gates, what are they? They are special function gates. Keep the heading. Next heading, special function gates. First one, exclusive OR gate. Keep the heading special function gates. In the special function gates, keep the side heading exclusive OR gate. Exclusive OR gate. Right. First, let us understand what is this exclusive OR gate for the two input case. Don't write anything. Please understand here. I'll give one point, then you write it. First, listen. 0, 0, 0, 1, 1, 0, 1, 1. What is the meaning of exclusive OR? It should perform exclusively OR operation. Means any one of them must be 1, not both. Any one of the input must be 1, but not both. Okay. But this is not the definition of exclusive OR gate. It is only satisfied for two input gate. If you have three inputs, how to say what is the XOR gate or any number of inputs? What is the XOR operation means? So please listen carefully. What is exclusive OR operation means? Whenever the input contains odd number of ones, then the output must be 1. Whenever the input contains odd number of 1, then the output must be equal to 1. otherwise the output must be equal to 0. Otherwise the output must be equal to 0. Right. Please write down that point first. When the input contains odd number of ones, when the input contains odd number of ones, then the output is equal to odd number of ones, then the output must be equal to 1. Then the output must be equal to 1. Otherwise it is 0. Otherwise it is 0. Right. So this is your XOR operation. So you can understand here how many ones are there? No ones. Here only one odd. Here only one odd. Here how many ones? 2 ones even. So whenever your input is odd number of ones, output is 1. Then it is called XOR operation. See here, this is the expression for XOR. Y is equal to, this is the symbol A XOR V. It can be written as A bar B plus AB bar. For time being, just understand this is the function, okay? But later when we discuss SOP and POS concepts, I will explain how you got this expression clearly. For time being, we can write like this. It is 1 for here and here. A bar into B, A into B bar. So that is 0, 1 or 1, 0 should occur in the input. But I will explain very clearly when we discuss about SOP and POS. Right? Now, this is your output Y, A bar B plus A B bar. Okay. This is the symbol for your XOR gate. A and B, A XOR B. This is the symbol of XOR gate. Here are some important valid points about XOR gate. They are very important. Listen. If in the XOR gate, one of the input is A, other input is 0, what happens? Other input is 1, what happens? Other input is A, what happens? Other input is A bar, what happens? If 3 A's are present, what happens? 4 A's are present, what happens? What will be the output? Using this, I'll give some conclusions also. If one of the input is 0, other input is A, what is the output of XOR gate? How can we say this? From the truth table. One of the input is 0. Other input is 0, what I am getting? 0. Other input is 1, what I am getting is 1. So, if one of the input is 0, other input is A, my output is A. Other input, whatever you have in the other input, same you are getting. If one of the input is 1, other input is 0, what is my output? Inversion 1. Other input is 1, what is my output? Inversion 0. So if one of the input is 1, output is inversion of other input, A bar. Yes or no? You can check. If one of the input is 0, what is the output? It is same as other input. If one of the input is 1, output is inversion of other input. Okay. Forget about the variables. Variables can be anything. Now A XOR A, meaning what? A and A means A can be 0 or 1. So 0 XOR 0 or 1 XOR 1. When both the bits are same, what is the output? 0 XOR 0 or 1 XOR 1. Both the cases output is 0. A XOR A bar. If A is 0, A bar is 1. If A is 1, A bar is 0. So 0 XOR 1 or 1 XOR 0, both are 1s. Now you see here, from this A XOR A XOR A. What is A XOR A? 0. What is 0 XOR A? A. Similarly, what is A XOR A? Just now we have discussed 0. Okay. Let me take one more A here. And A XOR A 0. 0 XOR with 0 from that truth table. 0. Here we can conclude also. A. How many A's? 3 A's. When n is odd, when odd number of A's are XOR, what is the answer? A. When n is even, when it is 4 or 2 or any number, when it is even, it is 0. When it is odd, it is equal to A. A XOR A XOR A XOR A up to n. If n is odd, my answer is A. If n is even, my answer is 0. These are the basic important points of your XOR operation. Okay, copy this. Right. That is about your XOR operation. The next one is exclusive NOR operation. We'll discuss that in the next lecture. Okay. We'll see the problems based on this XOR, XNOR and some NAND NOR gates, implementations and all in the next lecture. We'll see XNOR and the remaining part in the next lecture. Thank you.